So here is the exam 5 review that I promised in class today. So let's talk about it. So first off, we have fluids. So fluids, we're going to look at first fluids at rest. So for fluids at rest, first thing we had is pressure versus depth. So we have P1 is equal, or sorry, P2 is equal to P1 plus the density of the fluid times G times the height difference between the two. So if this is my point 1, this is my point 2, where this then is the height difference between the two. So that relates my pressure at point 1 to point 2. After that, we have Pascal's principle, which says that the pressure at one point is equal to the pressure at the other point, which means that the force per unit area at one point is equal to the force per unit area at another point. And as you have undoubtedly found out from the homework, that this is only true if they are at the same height. Otherwise, you do have to use pressure versus depth. So these guys have to be at the same position here. So my pressure 1 here must be equal to my pressure 2. Next off, we have buoyant forces. So buoyant force says that the force that an object is buoyed upward with has a magnitude of the mass of the fluid being displaced times g, which is the same thing as the density of the fluid times the volume of the fluid being displaced times g. So again, both of these two are only by the displaced fluid, not the total fluid, which is inside of the system here. So this is our buoyant force. So again, in this case, if I had an object, so here's my object, let's say it's partially submerged. So this guy's going to feel a buoyant force upward. So this is F of B upward, where in this case, the volume of the fluid being displaced is only equal to this volume here. So this is my volume of the fluid. And again, if it was fully submerged, then the volume of the fluid would be exactly equal then to the volume of the object. So that's pretty much it for fluids at rest. So for fluids in motion, first thing we have is the continuity equation. So the continuity equation says that the area times the velocity is equal to a constant. So all this means if I had something that looks like this, let's say tapers down to a smaller cross-sectional area, something along this line. So this is my area A1, this is my area A2, just means that the area times velocity V1 here must be equal to the area times velocity V2 here. So A1 V1 must be equal to A2 V2. Next up, we have Bernoulli's equation. So Bernoulli's equation says very similar, but this one says the pressure at a point plus 1/2 the density times velocity squared plus g times rho times the height is equal to also a constant. So again, all this means is that at any point, the pressure plus 1/2 the density times the velocity plus the density times g times y must be equal to a constant, right? So ultimately, it just means P1 plus 1/2 rho V1 squared plus rho GY1 must be equal to P2 plus 1/2 rho V2 squared plus rho GY2. So that's pretty much about it. So that's about it when it comes to things like this. Other than that, you do have the definition of density and pressure. So don't forget, pressure is the same thing as the force per unit area, as you can see from here as well. And that's pretty much it. And then density, as you know, is equal to the mass per unit volume. So that's it when it comes to fluid. So next up we have thermo. So our thermodynamics. First thing we really looked at was our expansions. So expansions. So first off, we have linear expansion, which says that the change in length is equal to alpha times the initial length times the change in temperature, where alpha, again, is just a material dependent constant. So all that means is here's my object to full at some initial temperature T0. If I raise the temperature, all that's going to happen then is this guy's going to increase in his length. So that's this part here. So this is delta L. Next up, we have area. So for the area expansion, we then have very similarly that the change in area is equal to twice of alpha, 2 because there's 2 dimensions, times the initial area times the change in temperature. And then finally volume. We have the change in volume is equal to either 3 alpha for solids times then the initial volume times the change in temperature, or that's also equal to beta times the initial volume times the change in temperature, where beta is typically only used for something like a fluid, right? So either a liquid, incompressible fluid, or a gas, right? So something like this. So good. So that's that. Let's see, what did we do after that? We did many, many, many things. Let's take a look here. So next up, so after that, next thing we looked at was, I believe, the ideal gas law, right? Yeah, so ideal gas law. So ideal gas law simply says that. So you can either write this in terms of the physics way or the chemistry way. So let's start off with the chemistry way. So chemistry way says somebody says that the pressure times the volume is equal to the number of moles times universal gas constant times the temperature. Or again, this says it's the energy for a mole of gas, where the physics way says that we have the pressure times the volume is equal to the number of particles times Boltzmann's constant. There we go, times the temperature, where, and again, in this case, this is the number of particles, where the number of moles is related to the number of particles by Avogadro's number. And that means that Kb is equal then to the universal gas constant divided by Avogadro's number. Good. So then we looked at the microscopic version, where the most important thing out of there is the RMS value. So in this case, we said that the RMS velocity, which is equal to the square roots of the average velocity, is then equal to the square roots of 3 times Kb times the temperature divided by the mass. So this is this guy here. Next up, we have mean free path. So the mean free path then is equal to 1 over the square root of 2 times pi times the diameter squared times the number of particles per unit volume. So in this case, d is equal to the diameter of the object. So if this is my object, then d here is the diameter. So good. So after that, then we started moving into ideas of heat in internal energy and all that different stuff here. So let's start off then with specific heat. So specific heat says that the heat then is equal to the mass times specific heat times the change in temperature. And again, this is true when we don't have a phase change. So no phase change. So in this case, all we're doing is we are changing, again, the kinetic energy. So the kinetic energy of the system is actually changing in this case. Next up, we have latent heat. So latent heat says that the absolute value of the heat is equal to plus or minus the mass times the latent heat, where in this case, the plus sign means that energy flows into the system. And then the minus sign here means that energy flows out of the system. So into would be, for example, when you have a solid going to a liquid, and then into would be when you have the liquid going into a solid. Right? So good. And a latent heat corresponds to, now this is when we have a phase change, which means we have technically two different latent heats that we're going to deal with, even though in nature we actually have three, but we have the latent heat of fusion. And then there's latent heat of vaporization. So again, these are specific numbers that correspond to the specific object that it is that we're looking at. So again, if we're looking at water, you'd use it for water. Any other object, you'd use it for that object. So again, this one is when I go from a solid to a liquid or from a liquid to a solid. And as we just said over here, this is then going to be plus, this is going to be minus. And then vaporization is when we have a liquid going to a gas or a gas going to a liquid. So, and again, in this case, the top one corresponds to positive and the bottom one corresponds to negative. Fantastic. So that brings us now to calorimetry. So calorimetry says that what? The total heat of a thermally isolated system, which is equal to the sum over all of the individual heats, must be equal to zero. So here we're assuming that this guy is thermally isolated. Now, of course, if it's not thermally isolated, that means we're losing heat, so we'd have to take that into account, but we're not going to do that in this class anyways. So good. So that's it. So calorimetry. Next up, we have work. So let's talk about work. In this case, I'm going to look at the work done by the gas. And again, the work done on the gas is just with a negative sign. So we said that the work done by the gas in general is equal to the integral from the initial volume to the final volume of the pressure integrated over the volume. And this is when our pressure is a function of the volume, such as in the ideal gas law. Now, if our pressure is a constant, then this guy becomes the pressure times the change in volume, which is when our pressure in this case is equal to a constant, meaning it is not a function of the volume. So good. So that's that guy. And then we also have now the first law of thermodynamics. So the first law now relates all these things together. So it says, how many different ways can we change the internal energy of a system? Well, that is, we can either have our system have heat flow into or out of the system, because again, heat, at least away from a phase transition, corresponds to the temperature, thanks to the specific heat. Or we can do work. And if we do work, in that case, then we're also going to change the energy, because remember, work is the same thing as energy. So in this case, I get cube and minus the work done by the system. But if you want to use the work done on the system, then this is Q plus the work done on the system, where again, the work done on the system is equal to a negative of the work done by the system. So that's our first law of thermodynamics. From there, we looked at our thermodynamic processes. So let's go through each one of those. And remember, these guys, make sure they definitely show up on your equation card. So these are our processes. So first off, we have isovolumetric. Volumetric. So this is when your volume is equal to a constant. So in this case, the PV diagram is just a nice vertical straight line. So this is my volume. This is then my pressure. So in this case, this is just going to be a straight line. So it has constant volume. Now, if it has constant volume, that means from the other side, that work then must be equal to zero, which means our change in internal energy must then be equal to the heat. Okay. Next up, we have isothermal. So isothermal is when the temperature is equal then to a constant. Okay. So in this case, if we look at our pressure versus volume, so this is now just going to be a 1 over V curve in this case. So good. So in this case, since the change in internal energy is zero, that means, or sorry, since the temperature is equal to zero, that means our change in internal energy is equal to zero. And basically the reason for that is, again, if I'm away from a phase transition, if I'm not changing the temperature, then I'm not changing the kinetic energy, and the potential energy stays the same as well. So in this case, we're not changing anything. But by the first law, this means then that my heat minus my work done by the gas is equal to zero, which means my heat then is equal to the work done by the gas, where the work done by the gas is the same thing as the number of moles times universal gas constant times the constant temperature times the natural log of the final volume to the initial volume. Okay. So that's our isothermal. Next up, let's see, let's go back to here for a second. So one other thing I should mention is my change in internal energy is going to be equal to the number of moles times CV, which depends on the type of gas, times then my change in temperature, where again, CV is equal to either 3/2 R, 5/2 R, or 7/2 R, depending on, in the first case, I have a monatomic gas. Second case, I have a diatomic gas. In the third case, we have a polyatomic gas. Good. So next up, we then have number 3, which is isobaric. This just means pressure is equal to a constant. So on my PV diagram here, so pressure and volume, in this case, we get a nice horizontal line. And that's pretty much about it for that one. Next up, number 4, we have adiabatic. So for adiabatic, the heat flow is equal to 0, which means that there's no heat exchange. My PP diagram looks very similar to an isotherm, but it's a lot sharper. So instead of like a 1 over V, it's more like a 1 over V squared. So this guy's going to 0 much quicker than that one is. So it's a lot sharper in this case. So here we know that we have some relation, so that the pressure times the volume raised to the gamma is equal to a constant. So again, it just means everywhere along this curve, pressure times volume to the gamma is equal to a constant. And we also have that the temperature times the volume raised to the gamma minus 1 is also equal to a constant, which again means anywhere along that curve, this is also true. Good. Where gamma is called the adiabatic parameter, which is either 5/3, 7/5, or 9/7. And again, the first one is for the monatomic, second one is for the diatomic, and the last one is for the polyatomic. So these are our quantities or thermodynamic processes that we care about. Next up, we had energy transfer. Let's do that in green. So for energy transfer, so for the transfer of energy, we had number 1, we have conduction. So conduction then simply says that what? The power, which is the heat per unit time, is then equal to kappa, which in this case is our coefficient of thermal conductivity, times the area divided by the length times the change in temperature. So this is the rate at which energy or heat is being brought from one side to another side. Second, we have convection, but that's just more of an idea, so we're not going to bother with that one. And then the second one then is radiation, where radiation says that the power is then equal to the emissivity, which is the difference that an object is from either a black body or from a perfect absorber, times sigma, where sigma is what's known as the Stephan's constant, times cross-sectional area times temperature to the 4th. So this is our power, or the rate at which energy is converted or transmitted from one to the other one. And then finally, we have our entropy. So this is our last topic. So entropy. So entropy, if I put a Y on there, says that the change in entropy is equal to, in general, the integral from the initial temperature to the final temperature of the differential heat divided by the temperature. And in this case, this is when the Q is a function of the temperature. Now, if it's not, so in this case, if Q is not a function of the temperature, meaning that in this case, for example, our temperature can be constant, then this guy simplifies then to the heat divided by the constant temperature. I'll just write those two down. That brings us then to the second law. So the second law then says that the change in entropy for a system must either be equal to negative or sorry, not negative, positive or equal to 0, meaning that it is equal to 0 for a reversible and then not equal to 0 for an irreversible process. Now, for an ideal gas, we then derived the change in entropy for an ideal gas. What we found was that for an ideal gas, that the change in entropy was then equal to the number of moles times the molar specific heat at constant volume times the natural log of the temperature divided by the initial temperature plus R, which is the universal gas constant, times the natural log of the final volume to the initial volume. So this is then our change in entropy. And then finally, we have our two efficiencies. So our real efficiency is then equal to 1 minus the absolute value of Q hot divided by Q, I'm sorry, that should be Q cold. Absolute value of Q cold divided by Q hot, or that's the same thing then as 1 minus the absolute value of Q out divided by Q in. Right, so the heat flowing in versus the heat flowing out. And then finally, we have our Carnot efficiency, where our Carnot efficiency then is 1 minus the lowest temperature. So T cold divided by our highest temperature, which is then T hot. So this is our Carnot efficiency. So basically, as we said in class, we went through all of the different problems that'll be on the exam, but definitely expect those things to be on there. Other than that, that's pretty much about it. So these are all of our different expressions. So feel free to go back and then pause when I'm writing too fast so you can actually see what I'm writing. But these are all the equations that are going to be on the on your equation sheet. Other than that, just remember that don't bother writing down all the different constants. As you can see, we have a whole bunch of different constants. Those, again, will be given on the first couple pages of the exam because it will take us, we have a lot of constants, so there will be a couple pages of exams, or not of exams, sorry, of constants on the exam. And I will give you some that you don't need and some that you do need. So just make sure you look up what exactly the object is when you use its actual uh, constant in this case. So yeah, that's it. So let me know if you have any questions. Other than that, I'll see everybody on Friday.